All right, listeners, get ready for a deep dive
Oh, yeah.
into this paper that's making some serious waves in the machine learning world.
It's a big one.
Probabilities-Informed Machine Learning. It's challenging some pretty fundamental assumptions
Yeah.
about how we train models and kind of hints at a future where AI systems aren't just hitting the accuracy mark, but are also deeply aware of uncertainty.
Absolutely. It really does highlight
Yeah.
crucial shift in thinking. For a long time, machine learning has been, obsessed with minimizing errors,
Yeah.
squeezing out every last bit of predictive accuracy.
Right.
But this paper is arguing that we've been missing a piece,
Oh, really?
a crucial piece of the puzzle, that inherent uncertainty that exists in so many real-world phenomena.
So it's not enough to just hit the target.
Right.
We need to understand the spread, the potential for error, the whole probabilistic landscape.
Precisely. And that's where this probabilities-informed machine learning, or PRIML, comes in.
I like it.
It's about building models that don't just make predictions, but also quantify their own uncertainty.
CRIML. I like the sound of that.
Yeah.
So how does it actually work in practice?
Well, it's not about inventing entirely new algorithms,
Okay.
but it's more about rethinking how we use the ones that we already have.
Gotcha.
PRIML takes a two-pronged approach. So first, it still uses the traditional error minimization techniques like RMSE to make sure we have good point-wise predictions.
Yeah.
But here's the twist.
Oh.
It adds a second layer,
Okay.
a CDF-based distance measure. This focuses on aligning the model's output distribution with the true distribution of the data.
CDF, that's the cumulative distribution function, right?
That's right.
So we're looking at
Yes.
how the whole ensemble of predictions match the underlying probabilistic structure instead of just individual predictions.
Exactly. It's about making sure the model isn't just getting the average right. It's also capturing, the spread, the tails, the entire shape of the data.
Right. Okay, that makes sense. But where does this probabilistic information come from?
Well, the paper outlines two main approaches.
Okay.
The first one is what they call empirical derivation. Basically, it means using historical data to estimate the probability distribution of the target variable. So for instance, let's say you're trying to predict equipment failure. You could use past data on failure times to estimate the probability of failure at different time intervals.
Gotcha. So we're using the wisdom of the past to inform our predictions of the future.
Exactly.
What if we don't have a lot of historical data?
Well, that's where the second approach comes in. They use something called structural reliability theory. And this means designing experiments and using reliability methods to estimate the probability distribution.
So we're actively probing the system to understand the behavior.
Exactly. And what's clever about this approach is that it serves a dual purpose. Not only does it help us understand the system's reliability, but it also gives us valuable data to train our PRIML model.
Interesting. So it's a win-win.
It is.
Okay, so we got the theory down. Can you give us some specific applications?
Well, they applied PRIML to both neural networks and support vector machines and tested it on a range of problems. One that I thought was really compelling was the structural health monitoring example.
So like a bridge or building.
Exactly. So imagine you're trying to predict damage levels in a structure based on things like load, vibration, material fatigue, and so on.
Yeah, a critical task for safety.
It is. And they developed a probabilities-informed neural network, or PRIN.
Okay.
And the results were, quite impressive, especially when they were dealing with limited training data.
So even with a small amount of data, PRIN could outperform traditional neural networks.
Exactly. And the key lies in this dynamic parameter they introduced called alpha. It basically controls the balance between prediction accuracy and distributional alignment during training.
Okay.
So think of it as a slider that adjusts how much emphasis the model places on hitting the target precisely versus capturing the overall spread of the data.
So it's finding the balance between accuracy and uncertainty awareness.
It is.
Did they apply PRIML to any other problems besides structural health monitoring?
They did.
Oh.
They also used a probabilities-informed support vector machine, or SVR, for image denoising.
Okay.
And they showed that by incorporating these probabilistic constraints, their approach could remove noise more effectively, but also preserve these important image details.
That's great.
It is. They even provided quantitative results using metrics like PSNR, which measures peak signal-to-noise ratio, and SM, which quantifies structural similarity.
Showing significant improvements over baseline and RMSE optimized models.
So they're walking the walk. They have concrete evidence.
They are.
Yeah, this is sounding like a really versatile tool.
Versatile tool. That's a good way to put it.
What about classification tasks? Did they look at that as well?
They did.
Okay.
They applied pre-mel to this classic data set called the ionosphere data set.
Okay.
And the goal is to classify radar returns as either bouncing off the ionosphere or something else.
Right.
And again, their probabilities-informed SVC model really outperformed the competition, achieving significantly better accuracy, precision, recall, and F1 score.
So it seems like this approach, this pre-mill approach, is giving pretty consistent results across different problems.
It is suggesting that incorporating probabilistic knowledge into machine learning can lead to more robust and reliable models, especially when we're dealing with uncertainty. It makes sense.
In limited data.
It's like we're moving beyond this era of black box predictions to a world where AI systems can not only tell us what they think will happen, but also how confident they are.
Exactly. That's a huge step forward in building trust and transparency in AI.
Now, before we go too far down that road, I kind of want to shift gears a little bit and get your historical perspective.
Sure.
Does this idea of probabilities-informed learning remind you of any similar shifts?
You know, it does remind me of similar shifts in scientific thinking. For centuries. The main paradigm in science was determinism. The idea that if you knew the initial conditions, you could perfectly predict the future. But then along came things like quantum mechanics and statistical mechanics, which introduced randomness and probability into our understanding of the universe.
It wasn't about precise predictions anymore. It was about the likelihood of different outcomes.
That's right. And that shift revolutionized physics. And I think it had a big impact on other fields as well.
Right. It's like we're seeing a similar paradigm shift now in machine learning.
I think so.
For a long time, machine learning was very much focused on finding like deterministic relationships in data. You know, think like linear regression, where you're trying to find the perfect line that fits the data points. But that approach can fall apart when you're dealing with complex systems where there's inherent uncertainty.
Exactly. And that's why this paper is so exciting. It's not just about tweaking algorithms to get a little more accuracy. It's about fundamentally changing how we're thinking about training machine learning models.
So we're basically saying that uncertainty is not just this nuisance to be minimized, but a fundamental aspect of real-world phenomena.
Right. And so instead of trying to eliminate uncertainty, we need to embrace it and build models that can handle it gracefully.
It's like the difference between trying to predict exactly when a coin will land on heads and understanding the probability of getting heads or tails over many, many flips.
A perfect analogy. And I think this paper, Probabilities-Informed Machine Learning, is a big step in that direction.
So we've explored the problem, the solutions, some applications, even a little historical context.
A little bit.
So now I'm curious, what are the real world implications of all this?
So imagine a world where machine learning models are not just accurate, but also reliably quantify uncertainty. This could revolutionize fields like medicine.
Oh, wow.
Where doctors could use AI to not only diagnose diseases, but also understand the probabilities of different treatment outcomes.
That would be amazing. No more black box predictions. But a clear understanding of the risks and benefits.
Exactly.
What about other fields?
Think about finance. Probabilities-informed models could help investors make more informed decisions by providing a more nuanced understanding of market risks and opportunities. Or what about engineering? You could use these models to design safer and more reliable structures by incorporating probabilistic knowledge about, material properties, environmental conditions, potential failure modes.
So it's a game changer for any field, where making decisions under uncertainty is important.
It is, and it's not just about better decision making. It's also about building trust in these AI systems. When models can accurately quantify their own uncertainty, it makes them more transparent and accountable.
That's key, because if people don't trust the AI, they're not going to use it, even if it could benefit them.
Right, and this paper really shows how probabilities-informed learning can help bridge that trust gap by creating these AI systems that are not only powerful, but understandable and reliable.
All right, so we've covered a lot here.
We have.
Before we jump into novel notions.
Okay.
I want to circle back to something you mentioned earlier.
Yeah?
About this paper representing a potential paradigm shift in machine learning.
It's definitely a thought-provoking idea.
Yeah.
I think it's worth exploring a little further.
So what would a full-fledged paradigm shift?
Well, I think first and foremost, we'd see a much greater emphasis on understanding and incorporating probabilistic knowledge into how we design machine learning algorithms. It wouldn't just be an afterthought or a specialized area of research. It would be, woven into the very fabric of how we think about and build AI systems.
Instead of just kind of throwing data at algorithms and hoping for the best, we'd be more deliberate about what we already know.
Exactly. And this would require a closer collaboration between machine learning experts and domain experts in fields like, physics, economics, biology, and so on.
So we need to break down the silos between different disciplines?
I agree.
And have a more integrated approach.
I completely agree. We need machine learning experts who aren't just mathematically skilled, but also have a deep understanding of the domains they're working in. And we need domain experts who are comfortable working with and leveraging the power of AI.
I can also imagine a shift in how we evaluate machine learning models. It wouldn't just be about accuracy and precision, but also about how well a model captures uncertainty.
Exactly. We need to move beyond simple metrics like RMSE and start using metrics that really account for this probabilistic nature of many real-world phenomena.
Metrics that can tell us not just how close the prediction is, but how confident we are in that prediction. And this would have an effect on how we teach machine learning.
I think so.
It wouldn't just be about building models that minimize error, but about building models that reason about uncertainty. Make probabilistic predictions and communicate those predictions in a way that's understandable.
It's a fascinating vision of the future of machine learning.
It is.
Where these AI systems are not just powerful, but insightful, reliable, and trustworthy.
And it sounds like probabilities-informed machine learning is a step in the right direction.
I think so.
Before we get too lost in the future, let's come back to the present.
Okay.
Are you ready for some novel notions?
Always hit me with your wildest idea.
Okay, here we go.
All right.
What if we took this whole concept of probabilities-informed learning and applied it to how we design and interpret scientific experiments themselves?
Intriguing. So instead of just collecting data and analyzing it afterwards, we'd be using these models to guide the experiment itself.
Exactly. Imagine a model that can tell you which experiments are most likely to give informative results. Based on your current knowledge of the system. That
could really revolutionize scientific discovery. Instead of, blindly stumbling through this vast experimental space, we could have an AI guide that helps us navigate towards the most promising avenues.
It's like having a super intelligent research assistant that can say, hey, based on what we know, if you tweak this variable by this much, you're likely to see an effect.
And it wouldn't just be about efficiency. It could also lead to more robust and reliable scientific findings.
Because you're incorporating probabilistic reasoning into every step of the scientific process.
Exactly.
I love it. This is
a really novel notion.
Truly novel notion. But wouldn't that require a lot of computational power?
It probably would, but that's what Moore's law is for.
That's true.
And the benefits for scientific discovery could be enormous.
I agree.
Imagine accelerating research in medicine, material science, climate modeling. The possibilities are endless.
I can already see researchers using these models to design personalized drug trials. Or optimize energy grids, or even predict and prevent natural disasters.
And maybe even uncover new scientific principles that we wouldn't have thought to look for.
That's the beauty of combining human ingenuity with the power of AI.
Right.
We might stumble upon discoveries that would have been hidden if we stuck to our traditional ways of doing science.
Okay, so there's our first novel notion.
Yeah.
Probabilities-informed scientific discovery.
That's a good one.
Do you have any other ones brewing? You know what? That one was so good.
Yeah.
I need a minute to process it.
Okay.
I think we should pause here for now.
All right.
And let that one simmer with our listeners before we blow their minds with another one.
I like it, leaving them wanting more.
Exactly.
That's the hallmark of a great podcast.
That's right.
So join us again next time.
Yes.
For part 2.
Part 2.
Of this deep dive into probabilities-informed machine learning.
I'll be here.
Where we'll unveil another novel notion that's guaranteed to spark your imagination.
Looking forward to it.
All right, we'll see you then.
See you next time. Yeah, that was a fascinating thought experiment.
I know, right? I can already picture researchers using Priml to design their experiments.
It would definitely change how we approach scientific discovery. But for now, it remains in the realm of novel notions.
Right.
Speaking of which, shall we explore another one?
Absolutely. I'm all ears.
Okay, fasten your seatbelts because this one might get a little meta. What if we could use probabilities-informed learning to predict and potentially even influence the evolution of human behavior?
Whoa, okay, you're talking about using AI to model and maybe even manipulate how people think and act?
Well, yeah.
That sounds like science fiction.
It might sound far-fetched, but the building blocks are already there. Think about all the data we generate every day, you know, social media posts, purchasing patterns, online searches, even our physical movements tracked by GPS and wearables. All of this data can be used to build a probabilistic model of human behavior.
So instead of just targeting ads based on our past behavior, we could predict how people's opinions and actions might evolve.
Exactly.
In our time.
Imagine a model that could identify the key factors that shape people's beliefs and then use that knowledge to design interventions that could nudge them in a certain direction.
That's powerful and a little unsettling.
I agree.
It could be used for good, like encouraging healthy habits or civic engagement. But the potential for misuse is undeniable.
It's true.
What if this technology gets into the wrong hands?
It's a valid concern.
Yeah.
Imagine a world where political campaigns or corporations or even authoritarian governments use these models to manipulate people for their own gain.
Right. That's scary.
It's a scenario we need to be very cautious about.
It's like we're at a crossroads.
I agree.
This technology could either bring positive social change or lead us down a dark path of manipulation and control. The stakes are high.
It underscores the importance of having these open and honest conversations about the ethical implications of AI. We need to establish clear guidelines and ensure transparency and accountability and involve the public.
This isn't just a technical challenge, it's a societal one.
It is.
We need to make sure that AI benefits humanity.
Well said.
And not just a select few.
We need to ensure that AI is a tool for empowerment and not a weapon for control.
Okay, so we've explored 2 really thought-provoking novel notions. Probabilities-informed scientific discovery and the modeling of human behavior. They're both fascinating and raise ethical concerns.
They do.
Before we wrap things up,
I
want to get your big picture perspective on this paper.
I think probabilities-informed machine learning is more than just a technical paper. It's a call to action. It's a reminder that we need to move beyond our obsession with just predictive accuracy and embrace the inherent uncertainty that exists in the world.
So it's about building AI systems that are not just smart, but also wise.
I like that.
Systems that can reason about uncertainty and make these probabilistic predictions and communicate those predictions in a way that is understandable and actionable.
Precisely. It's about building AI that's not just a tool, but a partner. A partner that can help us navigate this increasingly complex and unpredictable world.
That's a great way to put it. So as we conclude our deep dive into this paper, what is your final takeaway for our listeners? What should they be thinking about as they go forth and innovate in machine learning?
My advice would be this. Don't be afraid to embrace uncertainty. Don't shy away from that messy, probabilistic nature of the real world. Build it into your models. Make it a core part of your thinking. Because in a world of uncertainty, the most valuable insights often come from understanding not just what we know, but also what we don't know.
I love that. Embracing uncertainty. That's powerful.
And it's not just about being more accurate in our predictions.
Right.
It's about being more honest about the limits of our knowledge.
Okay.
It's about building AI systems that are not just powerful, but also humble.
Humble AI.
Humble AI.
Now, there's a novel notion, if I've ever heard one. Something to ponder as we all strive to create a future where AI and humanity can thrive together.
Well said.
Okay.
And who knows, maybe one of our listeners will be inspired to turn that novel notion into reality.
Right. After all, that's the power of ideas.
It is.
They can change the world.
Absolutely. All right, listeners, that concludes part 2 of our deep dive into probabilities-informed machine learning.
Looking forward to part 3.
We've explored some groundbreaking concepts, we've brainstormed some wild ideas, and hopefully sparked some thought-provoking conversations along the way. So join us again next time for the thrilling conclusion of this deep dive as we unveil another mind-blowing novel notion and wrap up this incredible paper.
Those were some pretty mind-bending novel notions.
I know, right? It's wild to think about how this whole idea of probabilities-informed learning could be applied in so many ways, but for now, I think let's bring it back to the paper itself.
Sounds good. Ready to wrap up our deep dive into probabilities-informed machine learning.
So as we're thinking about this paper, what are your final thoughts?
You know, I think the biggest takeaway is this.
Okay.
We need to change our mindset when it comes to machine learning.
It's not enough to just, go for predictive accuracy. We need to kind of accept uncertainty as a fundamental aspect of the real world and build that into our models.
So it's about going beyond just the deterministic paradigm and acknowledging that we can't know things for certain.
Right. We can only estimate probabilities.
And this has implications for how we design, train, and evaluate models.
Big implications.
It can't just give predictions as absolutes.
Yeah, right.
We need to be upfront about the uncertainty.
And that's where PRIML is so powerful. It gives us a way to build models that not only make predictions, but can also quantify their uncertainty.
Giving users the full picture so they can make better decisions.
I agree. And beyond just better decision making, I think this also leads to greater trust in these AI systems.
Yeah, when people know that a model has limitations, they're more likely to trust it.
Yeah.
Transparency and humility are key.
Yes.
It's not about building AI that's always right.
Right.
But AI that knows what it doesn't know.
That's a good point.
So where can listeners find the paper if they want to learn more?
You can find a link to the paper Probabilities-Informed Machine Learning in the show notes.
And as always, reach out to us if you have any thoughts or questions or even your own novel notions inspired by this paper.
We love hearing from you.
So that wraps up this episode of our deep dive into this amazing world of probabilities-informed machine learning. Until next time, keep exploring, keep innovating, and keep embracing the uncertainty. That's what makes it so interesting.
Couldn't agree more.